Yeah, as I say, my name is Bazaliy, and today I will talk mostly about securing iOS apps. My talk will be mostly practical, with a lot of code samples, including advanced ones. Few words about me. I work as iOS researcher and Blue Box security. I co-founded CocoHeads Ukraine, a community of iOS and OS X developers. It's mostly in Kyiv. And I open sourced to mobile security. If you want to find me at GitHub. What I will cover today. First of all, iOS security mechanisms. So how iOS security works. Next, we will check the security from attacker's point of view, how it could be attacked. How we could detect and prevent reverse engineering tools usage. And of course, security coding practices, including advanced ones. So, how iOS security works. First of all, it is a security boot process. Next is privilege separation, code signing, memory protection, sandbox, and encryption. How security boot process works. When you boot up your device, first of all, the boot ROM comes up. It's read-only data stored in a chip during the fabrication. It stores Apple public key, which is involved in checking each involved component. So boot ROM checking the signature of LLB, which is low-level bootloader. If it's okay, boots it. Low-level bootloader checks the signature of iBoot. If it's okay, boot iBoot. iBoot decrypt Apple logo, show it on the device, check the signature of a kernel. If it's okay, boots a kernel. Kernel enforce memory protection, code signing, ISLR, all the other iOS security checks. If it's okay, jump to application level. As we see, each step requires a signature check. If signature check fails, boot up is stopped. iOS uses a privilege separation for different processes like users, groups, and file permissions. For example, due to security reasons, Safari or Mail application run as mobile user. But the most important system processes or daemons run as root process. Code signing. In a few words, all application iOS should be signed by a trusted authority. If it's not trusted, kernel will not load the binary. This check is implemented in a kernel. After code signing in the Xcode, it is stored inside the binary in LC code signature load command. LC load signature contains superblob, entitlements, and signature itself. Superblob is a list of SHA-1 checks, SHA-1 hash sums of memory pages of your code. Entitlements store the non-default permissions and file groups of your application, and signature sign the superblob, not the whole content. Some internal Apple applications have not a signature, but the kernel have SHA-1 hashes of their superblobs. So that's why if you check it on jailbroken devices, Apple applications are not code signed properly, but it still works. Next, memory protection. iOS uses a policy memory cannot be executable and writable in the same time. So it could be only readable and executable. So processor can distinguish which part of memory is data, which part of memory is code. Check is implemented in a kernel, so it's not a user level stuff. In addition, executable stack and a heap are not executable for prevent exploits. All this stuff, unfortunately, vulnerable to ROP. ROP is return-oriented programming. That's why Apple, starting from iOS 4 and starting for iOS 6, implement address space layout randomization. When during a loading time, loader put in a random addresses, your binary, your shared libraries, heap, and stack. As a result of memory protection, there is no dynamic code generation for iOS. Next one is a Sandbox, or as it's called, a Seatbelt. It is based on Trusted BSD Mac framework. The check is implemented in the kernel, and it specifies profiles with some restrictions called operations. So, for example, there are a list of built-in profiles like no internet. That means that this application is restricted to use internet. Or container, all third-party applications that are downloaded from an app store use a container profile. Operations could be like read, write, search, and so on. And iOS 8, there are more than 100 built-in operations and more than 90 built-in profiles. In addition, Apple uses a system and user partition. So system partition is mounted as a read-only, and user partition is mapped as read-write. So you can download applications and store our data in user partition. And of course, encryption. In iOS devices, they have a dedicated iOS engine. So it is implemented as a hardware model. And in addition to iOS engine, Apple implemented SHA-1 hardware model. Apple uses device ID key and group ID key. Device ID key is a unique key for a device. It is stored during chip manufacturing. And group ID key is unique for a series of device processes. For example, A4, A5, A7. These two keys use it for generating 7 other keys that is used for decryption, like file system, iBoot, kernel, using in file protection. So these two keys cannot be accessed through a user mode. They are only accessible through hardware. Starting from iOS 4, Apple add the data protection API. Then you can mark your files or a keychain as data protected, and hardware module will do the rest for you. If you specify a passcode or a Touch ID key, these two keys are used in encrypting like a file system key. So the 7 derived keys are protected with a passcode. So if you not specify a passcode, all the encryption is useless. And this is how a remote device wiping works. So Apple just remotely remove a file system key. So it makes all the file system unreadable. Next is the security from attacker's perspective. I will talk about code injection, function hooking, login, Objective-C methods, a few ways to bypass a jailbreak detection or security checks. What is a code injection? It is an attack type which consists of injecting untrusted code that will be executed by application in the future. The most popular code injection is dynamic library injection. It could be injected by dynamic loader using DLD insert libraries. It could be injected by Debugger, LLDB, by Cycrypt, by specifying load command or a mobile substrate. I will talk about each of them more detailed way. There is a trick in a dynamic loader from OS X and iOS. We can specify environment variable DLD insert libraries and specify our library name, and dynamic loader will do the rest for you. So it is preload any library into your process. Of course, this stuff works only on jailbroken devices, but attackers, as you know, mostly use them. Next one is LLDB or GDB. You can run a remotely debugging session for your device. In my case, I SSH to iPhone, run debug server with specified port 1234, then run LLDB on my Mac, select platform remote iOS, connect to my device address with a specified port, and use DLOpen function. DLOpen function is part of dynamic loader, and it is allow you to add library to already loaded process. You can do the same with a Cycrypt in much easier way. So just inject a Cycrypt into application and use the same DLOpen to preload your library. You can even add a new load command. Why this trick is really interesting, it will even work on non-jailbroken devices. So you can inject your code on non-jailbroken devices. You can modify a binary, add a new load command with specifying a path of your library, and then reassign it, and it will work. The load command that could be used for this is lc load dilib or lc load weak dilib. There are a few tools that automate the process, like op-tool, insert.lib, and jailbreak. If you're interested, check it on the GitHub. And mobile Substrate. Mobile Substrate for now is the most popular code patching framework. It's allows you to hook C, C++, Objective-C, Java code. It uses trampoline for hook a C code, use swizzling or interposing for hooking Objective-C. It supports dynamic code injection with the filtering support. A quick overview of mobile Substrate API. By the way, maybe anyone have used the mobile Substrate before? Know what it's used for? Right now it's a main base for all the jailbreak tweaks. So mobile Substrate API provides APIs like get index of loaded image by ms get image by name. We specify an image name. Image it's like shared library. It returns the index in loading list. ms finds symbol. Return your address of a symbol in application memory. For example, I want the address of open function. So ms find symbol help me with it. ms hook function, you can hook any C or C++ function by specified function name, by specified hook address, and by specified a storage when the original values could be saved. Last two APIs work for Objective-C code. We can hook a message in a class with specifying the storage for original values, and we can hook the entire class. So we can replace NS object class for like my NS object. It will replace all the methods. Mobile Substrate support a loader, which is looking for library mobile Substrate dynamic libraries, iterate through each library, check the plist values, and load everything into memory. So we can even add the filters, like inject this code only if executable name is media server D, or only if bundle ID is com apple mobile SMS, or even only in binaries that have class tracking manager. A really quick theory about function hooking. So in ideal world, function main call function qsort do some stuff and return a value. If we hook a qsort, the main will, when calling qsort, will jump to a hooking code. So hooking code could change the input arguments to a qsort, so we cannot trust of the qsort returning a value. Or even hook cannot not call qsort at all. You can fake the return value and return to main. Here's an example of hooking NS object description. So I'm hooking description method and adding the explanation mark to a description string. As you see, I've used ms hook message x, specifying a subject class, selector, and my hook address. Let's check more usable example. As we remember, Objective-C code invoking Obj-C msg send C function to call all the methods. If we can hook Obj-C msg send, we can log all the Objective-C runtime, all the methods, all the arguments. This is a few implementation of it, like Aspective-C, Subjective-C, or Inspective-C. In my case, I'm logging IPIN application. And as you see, all the arguments like secret password, like pins, like sample pin node, everything that is specified as method arguments could be logged. So Objective-C is not secure. Function hooking could be used for bypassing jailbreak checks as well. In this example, I'm bypassing the system check. System check, if we run it on a jailbroken device, it will return non-zero value. On non-jailbroken device, it will return 0. So I'm hooking a system and return always 0. So if you use this check in your application, it could be really easily bypassed. The same is for files check. The famous jailbreak check for CIDEA files, check for SSH files. I can hook file exit path, and if the input argument is like application CIDEA, return 0. If not, invoke the original file exit path. The same for a fork. Fork trick is used for jailbreak check. So with fork, you are trying to create a new process. On non-jailbroken device, system will not allow you to do it, but on a jailbroken device, it will. So I'm hooking a fork and return always -1 that forking is not allowed. But in a real, it could be a jailbroken device. The next trick is goodly documented on the iPhone wiki. They say that if you use DLD image count and DLD get image name to iterate which dial lips are currently load, and say that it's very difficult to patch. As for me, it's not true. You can easily hook DLD image count and always return the image count -1 by hiding your library, and hooking DLD get image name. And if the index of the image that you should return is your image index, you return in the name of next image. So, in other words, by hooking this function, I'm just hiding it from loaded list, but in a result, it exists. It exists and working. There is a ptrace trick when you can specify ptrace with ptDNA attached. This code will crash, will detach any debugger, Xcode as well. I can bypass this trick easily by hooking a ptrace, and if the input argument is ptDNA attached or pttrace me, just do nothing. Otherwise, I'm calling the original ptrace. Function hooking could be used even for bypassing SSL pinning. You can hook the low-level SSL functions like SSL handshake, SSL station option, SSL create context, and specify that SSL check should not be performed. The implementation of this is SSL kill switch, so you guys can check it, how it's implemented. It's open sourced. There are even a few tweaks that allow you to bypass most well-known jailbreak checks just on the fly, like a TS protector, Xcon, or officer. It is hooking the system libraries. And for example, if you're trying to check for is application side exists, it will no, and so on. It's very similar that I showed you before. There are a type of tweaks that called the tracing tweaks. It's hook all the functions in a system and put everything to a log. So in my case, there is a log of security function CCK derivation when you transform in your key for something else, and all the input arguments are stored in a log, like the derived key, the specified algorithm, even a password, salt, and count of rounds. If you're interested, check Introspy, Snoop-It, or iSpy for more details. So, as you see, the reverse engineer arsenal is wide, and if we can detect a reverse engineering tool, we can prevent its usage. So I will talk about how we can detect debuggers, how we can detect hooks, how we can detect the code injection. The next trick shows the usage of sysctl function. We can use a sysctl. We can use a sysctl to get the current process flags, and if the flag ptraced is set on, we are under debugging session. So Xcode sets this flag when you debugging your code during debug. Next one is checking for a parent process name. So as we know, the main process in iOS is launchd. So all the processes, it launch all another processes. In case of debugging, the parent process will be not launchd, it will be debug server. So again, we get sysctl checking parent process ID and getting the parent process name. If it's not that we stored launchd, we are under debugging session. Next trick show how to detect a breakpointer. Breakpoint is in ARM architecture is specified by FEDE byte sequence. So we can check for like a first 10 bytes in each function. If it have a FEDE byte sequence, it is a breakpoint. We can even detect a function hook. In my case, I'm detecting Objective-C swizzling using a dladder function. Dladder function will show you the image where the pointer loads. So in this code, I'm checking a pointer if it's not from system library or not from user lib, where the all system frameworks are stored, it is hooked. The same technique could be used for detect a trampoline. Trampoline is when attacker modify the few bytes of a function and specify a jump to another function. So we can check first 4 bytes. If the first 4 bytes encoding is jumped to another place, and this function is hooked. We can even detect code injection by iterating through all environment variables. In my case, it's DLD insert libraries. And if we detect DLD insert libraries in release mode, 100% it is a code injection. But be careful with debug mode, because Xcode uses this trick internally for memory debugging. So it preloads a few debugging libraries in your process. We can even detect mobile substrate by iterating all the loaded images and checking for a specified name. But be careful, as I showed before, it could be easily bypassed. So check for a function hook before. The next trick show how we can detect like a bad symbols. In my case, I'm detecting a Cycrypt application. When Cycrypt is preloaded or injected in the application, it uses Objective-C classes for some functionality, and Objective-C symbols became a part of the global Objective-C runtime. So we can check in a global Objective-C runtime, hey, do you have a class with like CG, JS array, and selector init with JS object? If it returns a pointer to this method, the Cycrypt is preloaded into memory, so we are under debugging session. I will show you how to prevent hooking, patching your code, and how to add some obfuscation. Hooking. The best anti-hooking protection is to inline your function. So during inlining, compiler will not store the function body and create a symbol for it. It will wrap all the function body inside another function. So attacker cannot rely on a symbol for finding address. If it's not possible, make sure that you strip all the symbols from your binary by specifying like visibility hidden for a symbol. So it will not store the symbol, it will store like sub something. It will not readable for attacker. If first and second method not allowed for you, make sure that you detect a hook by DLadder and trampoline, as I showed before. We can check checksum for a code section by loading into memory, iterating through all loading commands, find a pointer to a code section, find the code section size. In my case, I'm checking SHA-1 hash of code section and comparing with a previously saved one. So if it's not equal, that means that someone fetched my code in a memory or on a disk. The next subtopic is obfuscation. So obfuscation is a process of transforming your code into a code not readable by attacker. So in my case, I'm hiding C function calls. So on the top, you can see that I'm calling DLD image count. Then I call DLD get image name. I can do the same, but retrieve a DLD image count address just in runtime. So I'm using DLSim. We specified DLD image count as a C string. Get a pointer, cast this pointer to function prototype, and use the original function. The trick is that you can obfuscate the C string. C string could be easily obfuscated. I use the same trick for hiding Objective-C method calls. So I can call uppercase string on an S string, or I can do the same by registering a selector with cell register name, specifying a string that could be obfuscated, and using obfuscate for invoking my method. As we talk about string obfuscation, there are a few ways how to obfuscate a string. As for me, the best ones is like a simple XOR or encoding decoding tables when you changing a symbol I for a symbol B, symbol C for a symbol D, so the string length will be the same, and it's really good for performance. If not, you can even use some crypto algorithms. In my case, I'm XORing an S string by getting each symbol on a string, in the first string and a second string, and use XOR to obfuscate it and turn a result. So if you plan to obfuscate all your strings, much better to use XOR or encoding and decoding tables. It will be much faster. You can even obfuscate numbers. So numbers are widely used as function arguments, and if you want to make it much harder for attacker to understand what you're doing here, we can translate your number through like some simple math function. In my case, what I'm doing, I'm specifying initial big seed value and doing some multiply, ORing, byte shifting. As a result, I get a result of 2. So what I'm doing, I'm generating the seed numbers before. It could be like a few thousand seed numbers. And each time I can specify a different implementation of number 2 obfuscation. I will share the code just after the talk, so you can try it by yourself. Of course, there are third-party obfuscators. A really good one is Encryption. It's a commercial solution. It provides a really great level of obfuscation, anti-tampering, debugger detections. So yeah, it's really good. There are a free one, LLVM obfuscator, that works on intermediate representation level. For now, it supports instruction substitutions. It supports flattering control flow, but unfortunately, it's not stable. I've played with it for a few months, and it still have some bugs. Another one is iOS class guard. It uses a different approach. It's analyzing your class names, method names, and so on, and generating some random replacement for it, and use defines to obfuscate or replace your real string with unknown one during a compile time. So as for me, it's a good addition to LLVM obfuscator. They works together really good. Next, I will show you some advanced techniques, such as function replacement, system calls, detecting device anomalies, and even how to obfuscate your assembler code. So what's the problem with the standard functions? So attacker can easily hook the standard library functions like memory compare, string compare, and so on, and you cannot trust them. In my case, I decided to re-implement it by my own and strip symbols. It's not too hard because Apple store the source code for 06 libc implementation, so you can take most of your code from open source Applecom. I made the same for a dynamic loader. I've re-implement DLSim, DLEader, DLDGetImage. So instead of calling the system ones, I use my ones instead. So attacker cannot hook it. In this example, I use DLEader. It is a DLEader implementation. I use nlist to get a symbol table offset and getting symbol addresses by indexes. So as I say, you can try it by yourself running init code. Next, you can check for not well-known device anomalies. As I said, you can check for a ptraced flag using a sysctl function. You can check even for pdisable ISLR. All iOS binaries should have ISLR flag enabled. Apple required it. If it's not turned on, something wrong. You can check even for Debugger flag, which specified a debugging section. You can check for mobile user ID and group ID. It should be 501. If it's not 501, it's something wrong with your device. It looks like it is jailbroken and hiding it. And the most advanced ones from my side is syscalls. Syscalls, it's how program requests some service from operating system kernel. It could be creation and execution of a new process, or some file operation and so on. Syscalls are implemented as a syscall function in libc, and in assembly level it is implemented as SVC instruction. That means in ARM terminology, entering a supervisor mode. So you should put the syscall number in R12 or X16 registers, then put some additional arguments to registers, and enter a supervisor mode. All the syscall numbers listed in the syscall. I will show you how it works. So in this case, let's check some function, in my case a read function, in disassembly. As we see, it stored the number 3 in register R12 and called the supervisor mode. So all the functions, like read, write, and so on, at the very, very, very low level, they use the syscalls. So every function is just a wrapper with some additional functionality, but at the very end they use the syscalls. Here, as we can see, number 3 is sysread. So yeah, it stores sysread syscall and asks kernel, hey, provide this functionality for me. With the syscalls, you can even access for some private stuff, like CSOPS or ptrace that are not stored in Apple headers. For example, with CSOPS function, you can check who is the signer of your code, what is the hash of your code that is generated by a code signing, even what is the certificate name of the signer. So use syscalls with sys CSOPS. We specified a buffer. In my case, I'm specified a SHA-1 hash 2. And we can go even deeper. We can re-implement all the functions by using the syscalls. In my case, like getPid, I replace it with syscall, getPid, sysdetail with syscall, sysdetail, and so on, so on, so on. So it will be much, much harder for attacker to debug and trace this code. And we can go more deeper. We can implement our own syscall. So I implement my own syscall function in assembly. Use R0, R2 register for storing arguments, R12 for specifying a syscall number, and calling and SVC instructions. What's the problem with it? For really, really skilled attacker, it's not a big deal to understand even assembly, and it is SVC, it is entering a supervisor mode, looks like this guy is using a syscalls. We can do some interesting trick. So iOS and ARM architecture have a different modes. For example, ARM mode, SAMP, SAMP2, and ARM64. And the instruction length is different for these modes. For example, for ARM it will be 4 bytes, but for SAMP or SAMP2 it could be 2 bytes or 4 bytes. So we can implement a few instructions in a different mode, and the assembler do not know how to switch between this mode. So in my case, I use a trick called instruction overlapping. Just before entering a supervisor mode, I'm adding some random data like byte and so on. And this assembler will think that instruction length should be 4 and trying to disassemble this data as a part of instruction. So how it works. As we see, there is no SVC instruction anymore. This assembler thinks this like LDR instruction, but in a real, it calls a SVC instruction. So why we use this way, it's not so easy, but because the intermediate representation not allow you to modify inline assembly code. So you need to do it by hands. To summarize what I'm saying, do not rely on iOS security, even on Objective-C or Swift. By the way, a few words about Swift. Swift could be easily hooked too. Swift works as normal C, C++. program. So it could be hooked, it could be debugged, and so on and so on and so on. If you making a security code, think about the environment that will be run as everything is hooked environment. So you cannot trust any system function before checking it. Detect hooks and code injection, detect debuggers and device anomalies. If you need to implement standard functions, allow and use syscalls. Syscalls are really, really great. And obfuscate your code. As a final words, I can say that cracking time usually equal to protection time. So if you spend just 15 minutes to protect your code, the skilled cracker will spend 15 minutes to crack this code. So make a balance between security stuff and implementation time. That's all from me for today. Maybe you guys have some questions. Yeah.
We have a couple minutes for questions.
Okay, thank you for your talk. Seems you shared a lot of tricks. Do you have some more tricks that you don't share?
Yeah.
So, because you know, probably potential hackers are here on the audience. So, how is it? Do you share everything or?
No, I'm not sure everything. So I have a good tricks for hackers who can try to crack my code. So I was trying to, as I said, to make a balance between how this code could be easily to implement and decide should I share it or not. So I can add more assembly, inline assembly examples, but I'm not sure that it will be really good for everybody because it's very processor specific and so on. Yeah, if you have questions for some additional checks, you can catch me after.
I think I know at this level. Okay, can I have one more? And for example, you detect debugging, so it means that yeah, I don't know, you close the application or something like this. But in the development mode, doesn't really, you know, oh, my security check, I cannot debug my application. How often this happens?
Yeah, so you should use like if-def debug. So during the development and the debugging section, it will be specified by Xcode, this preprocessor macros. So I'm usually disable all my security checks by if-def debug, and they are not run it at all. And what else? Yeah, some checks like detection for a debugger, be careful with it. So you can even not able to debug it with the Xcode if this check is enabled. Yeah, please.
Hi, do you have any experience with Apple review process for apps built with techniques you presented, like hooking, detection of hooking, or even calling syscalls instead of invoking calls provided by operating system?
All these checks are absolutely legal, so we use them in a non-jailbroken environment and apply for Apple review. Better not. As I remember, the last time Apple did not really like syscalls if they implement it as libc invoking. But if you implement that in assembly, they will not find it at all. So Apple use just a static analysis. It analyzes only your symbols in your application. If they're not found nothing suspicious, they pass you. So you can add a lot of bad code by assembly, and they will not find it.
I have a question about the LC load command injection. So you can inject a delib which has a constructor in which you can load something before actually the app is loaded. So is it possible to replace those system calls, which are, for example, which you can use, for example, to check how many load commands there are and if it's the same number that your app is using? So if there are any additional load commands added, injected somehow. can you replace those system functions before the app is loaded?
It is possible. There is no system calls for this feature. It is possible by calculating it by hand from a header and store it inside the binary. The problem is it will be different from each architecture. For IRM and for IRM64, this number will be different. And it could be patched too. So skilled attacker, after adding a new load command, after load into memory can write back the original numbers of load commands in your header. So after a loader will pass the application. It will be completely legal from a system point of view, and you cannot detect any injection. So that's why you need to use the as low as possible function as assembly, because it is not possible to hook. It is possible, but attacker should write a lot of stuff in a kernel. It's too complex. Yep.
Talk loudly. If you, I mean, you can just search and replace for your system calls.
Mm-hmm.
How do you protect against that?
Yeah. So what if attacker use a search and replace for SVC instruction? Yeah, I'm use anti-patching code checksums. So even if attacker can find it and understand what I'm doing here, he cannot patch it. He can patch it, but my security checks violation will say, hey, no. So it's like cat and a mouse. So you add more checks, attacker bypass more checks. You're doing checks on the checks and so on. It depends on what level of security you need. Right now, the future of all, from my point of view, the future of all mobile security will be during a LLVM, intermediate representation level. So on this level, you can add a lot of checksums for your code, the checksum that check a checksum, and so on, and so on, and so on. It will be generated automatically, not implemented by hand, which is much more complex. So you can checksum just every, I don't know, every 2 kilobytes of your code and cross-check this stuff.
I have a question also. Here.
Yeah.
How converting to ARM64 affects all this assembly fun with system calls? It
will be even easier than ARM, because original ARM architecture allows you to put no more than 4 arguments directly in registers. If there are more than 4 arguments, you should put them on stack. But ARM64 allows you to put up to 7 arguments in a register. So you just directly put it to x0, x1, x2, x3, and so on. Put the system call number in x16 and invoke the same SVC instructions. So it's easier than on ARM64 than on ARM.
Okay, and this random system calls of some adding numbers and moving from one register to another when you're overlapping, does it not break any method calls involved in higher level? You are rewriting some values in register. Does it not affect all the code?
No, because I'm placing like a data between 2 assembly instructions. So when executing, the processor knows that instruction length is 4, and just skip my next 2 like trash bytes. But this assembler understands it as an instruction part and decode it as an instruction. So the code that I showed with instruction overlapping is completely working.
Could you point out an example of the best protected application in the App Store?
I think the Square guys do a really good. At Bluebox, we're trying to do some interesting tricks, but we have not released it to like a public yet. I think the Ericsson protected applications are good.
What's your favorite disassembler?
Right now I'm using IDA because it depends what you need to crack. For C, C++ code, IDA is the best. For Objective-C and for Swift, right now, Hopper disassembler have more features. I really hope that IDA will add Swift support soon. But right now, only Hopper can normally demangle the Swift names.
Okay, well, thank you, Max, for your talk.
Thank you, guys.